Is in the second session of this morning, Michael Ferris is going to give a talk about 100% renewable electricity. We don't have a nemesis for Michael Goran-Strabak arrived yet, but I think Ben Hobbs is going to stand in for Goran.
So I had put out a contract, and it seems to be effective to get rid of the nemesis. You know, mafia and money deals with the problem, right?
Financial contract?
Financial contract, yeah.
Over to you, Michael.
Right. Thank you very much. So this is joint work with Andy, and about a year and a half ago, I went to Auckland, New Zealand, fully excited about spending 6 months there and going swimming and surfing and sailing. And then within 3 days of getting into New Zealand, the Prime Minister, who's been very popular in the popular press, or very visible, at least recently in the popular press, was also very visible at that stage. So Jacinda Ardern had gone into an agreement between her Labour Party and the Green Party, and one of the outcomes of that was something that ruined my sabbatical leave, and that was this request to the Climate Commission to plan to transition to 100% renewable in electricity by 2035. So Andy, being the former advisor that he was, said that we have to work on this. So bang goes the swimming and everything. Cool. So as politicians do these things, they have, you know, they say, they put the caveats in here in the statement. So this is a document. I'm not sure that the name of the document is exactly correct, but in the document they say, let's get 100% renewable electricity by 2035. And renewable includes geothermal, just because geothermal is a big thing in New Zealand and we can't exclude it. And then they said, in a normal hydrological year. So I'm going to have to explain to some extent what both of those things mean. And then there was the idea, of which has been prevalent at this whole conference, is that the idea was that they were going to stimulate up to $1 billion of new investment in low carbon industries by this drive to 100% renewable. And they had the carrot, which was the investment fund of about 100 million, so a tenfold increase. So, what does this question, I'd like to at least tell you today what this means. So I'd like to talk about what does fully renewable and electricity mean, but before I do that, I'd like to give you a view of the picture and the underlying model and the data that supports this model. So this is my picture of New Zealand. New Zealand actually has two islands, the South Island and the North Island. So S is the South Island. That's the place you should go if you're a tourist. So that's where all the nice mountains and everything. And also within the South Island is this huge infrastructure of hydrology and dams and all of the backbone of the hydroelectrical system is on the South Island, and that's depicted over here. Most of the people, and therefore most of the demand, live, or 40% of the people live in Auckland, which is in the North Island. And so I have depicted the problem that we have to get the supply to the demand up here in the North Island. And so, as there are two islands, there's this other node in my very simplistic transmission network here, which is depicted by H. You could think about this as being halfway, but it's not halfway. It's some name of some, I always forget, the Hayward's power station, right? So this is just on the North Island. And so this transmission line is actually something which goes under the water, and they're worried about this being a capacity link, which is actually going to cause congestion, and there's lots of stuff. So I'm going to build a simplistic model, and that simplistic model is going to deal with transmission very simply, because I don't want to just solve small models. I actually want to solve models that are going to be rich enough that we can capture all of these effects that you've all been talking about. So I would like to talk about risk, I'd like to talk about multiple agents and some of that. So at some stage I have to make some approximations, and here's one approximation I'm doing in the transmission capability. It's just data. So then there's the other thing, and so if we're going to 100% renewable, where's the non-renewable stuff? Well, the non-renewable stuff is this great big Huntley power station, which is has some coal and some gas production, and that's the thing which is potentially on the chopping block here. Okay, so underlying that is modeled. But then what does fully renewable mean here? So does it mean that we actually want to permanently shut down all of these plants here, just get rid of them, shut them down? Or does it mean that somehow we want to control the greenhouse gas emissions from electricity generation? And the purpose of this talk is to actually think about models and show that those two things are not the same, and actually try to think about how we would quantify the differences and what we could do about that. So first of all, there was the problem of the advisor, and then there was the problem of the student. So Andy had this really clever master student who then looked at this problem in terms of simulations. So he ran a huge number of simulations of what would happen if you ran full Huntley on across a whole bunch of different scenarios, if you shut down gas in Huntley, or if you shut down gas and, you shut down coal in Huntley, and here if you shut down the coal and the gas in Huntley. So just let's cut down capacity. So we're going to cut down capacity by closing it. And then what actually happened in that system? Well, I'm going to show here a whole bunch of scenarios. He ran huge amounts of computation and looks at the stored energy, which is the stored energy in those hydros that he has under all of these different scenarios, and then generated these wonderful stored energy pictures in all of those three scenarios. What can you see is you can see hedging. So in here, this is the standard thing, and the distribution is actually lower than the distribution when you have gas. You're actually storing more water. And then here, if you have nothing at Huntley at all, then you actually have even more hedging. You're going to store more water behind your dams. And so the key point here is with low renewable plant capacity, low non-renewable plant capacity, you've got rid of the stuff that, as we've all been talking about, is fast reacting. Then what happens is you can't wait to the last minute, and so at certain times of the year, you leave your reservoirs a lot fuller so that you have the ability to act what if, in case we have a dry, or in case they have a dry winter. And so the upshot is that closing down the plants, you actually reduce the capacity of the thermal, but then you use it more frequently in order to maintain the levels in these reservoirs. And in using it more frequently, you then, in order to maintain those levels, you use the thermal more frequently, and you end up emitting more carbon emissions. So you have this trade-off that shutting down plants, capacity reduction, is not the same as controlling CO2 emissions, and that's what we have called the Fulton effect. But this model took a long time to run. It had lots of detail in it, simulation detail. And what we would like to do is think about, well, instead of shutting down Huntley or whatever, what is the portfolio of technologies that we would actually like to build within our system? And so if we want to that we need to have a model which captures this effect, because if it doesn't capture this effect, it's going to be nonsense. But it also has to be small enough and nimble enough that we can use it in contexts of equilibrium problems or stochastic planning problems of the like that we've heard all this week. So that's what I'm going to talk about here. So the key point is that we have uncertainty here within our model at multiple different time scales. You have the capital cost expenditures, long-term uncertainties, and all of those things. You have seasonal inflows. So this is the dry winter issue. And so with the dry winter, I'll think about those as coming on the periods of weeks. And so that's something like a medium-term uncertainty. Then you have wind and solar generation, which are short-term uncertainties. You can predict that probably at the level of half an hour, and so we'll think about that. And then you have the random variation due to failures and something like that occurs at seconds. And yet we have to, so we're having to trade off all of those uncertainties and build a model which needs to capture all of those things. But again, still, we want these models to be nimble, maybe so that we can solve them on our laptops, or maybe we can solve them effectively, at least within a day or something like that. Cool. So we built a two-stage stochastic model. So the key features of a two-stage stochastic model are that we have the capacity, so we have the capacity decisions are the first stage decisions. Those are our variables Z. K of Z is the cost of that. And then we have a second stage within this model, which is operational. So within the operational, we're going to have a whole bunch of different scenarios, and then we're going to actually worry about those scenarios determining a random demand, and then we're going to talk about the expected costs within the second period. So we have the second period, we actually have the fact that we'll generate at the level Y in the scenario omega, or in the future omega, or we'll have to do some load shedding Q, and we'll value that load shedding at the value of lost load, which is this variable V. Maybe I can choose it endogenously, maybe I can choose it exogenously. Let's not worry about that. So in principle, that's the model. And then we're actually going to impose on this, and we're going to think about what does fully renewable mean. Well, we're going to think about fully renewable by imposing this constraint. So in here, I can think about the Z non-renewable being the capacity of the non-renewables, and that capacity is going to be constrained to be less than or equal to the level in 2017 multiplied by some factor 1 minus theta. And as I make theta bigger, as I increase theta, I'll make this a tighter and tighter constraint on capacity, which we maybe have already decided is not a good constraint, but because of the Fulton effect. But we can actually impose that and think about valuing this with different values of theta. Cool. So then what's the line? Well, then you actually want to worry about what are the costs. So now in this picture, I'm showing you the costs. So this is business as usual in 2035 with all of the planned closures already put into the model, with a new demand, which is an estimated demand that Andy did lots of work on to actually determine what's the appropriate demand in here. And so this is the cost. Then this is the cost of 50% reduction in those, in this case, emissions, CO2 emissions, and then 75%, 90%, 95%, and here's the whole 100%. So you can see that the cost is going up significantly, and as we've said, so this is mom and apple pie to everything for you here. The costs are dominated by the investment costs, and the operation costs and the maintenance costs are going to be difficult to recover those investment costs. That's what we've all been talking about here. So there is, I also separate out lost load. And if you change, so as you talked about yesterday, if I change my data, so if I don't have as much consented wind within New Zealand and change those values, then this line of lost load here can actually increase or decrease. So this is data dependent, and while we're actually presenting results which I think are informative to actually produce results for the New Zealand government, we would have to, we or they would have to run with much more extensive runs of this and look at sensitivity of this. So as we've been talking about here, how to recover those fixed cost investment, I will defer to all of you guys to do that better than I. Okay, so that's the costs. I was lying. So I was lying that my model wasn't quite as simple. It is a two-stage stochastic program, but it wasn't quite as simple as that, because I have to deal with a lot of other issues in terms of this uncertainty at different rails. So I'm going to talk about that model. Again, it's a two-stage model, and so here you can think about the investment as being capital plus capital investment plus maintenance investment. So I invest new capacity xk, that costs kk, and then I operate at level zk, and that operate at level zk has a maintenance cost. So I actually keep open things, and I have to pay a maintenance cost for that. So we actually have some nice linear constraints on that. That's the red constraint. I will come back to this variable w here, which is also a first stage variable. And the reason we incorporated this into our model is to make sure that we could capture that Fulton effect. So WT is that we're going to say that that within our model there are a certain number of seasons or certain points of time when we're thinking about reservoir management, and at those certain points of time we're going to make a first stage, kind of a capacity or a first stage decision, which is going to be the target level for the reservoirs at that time. So not only are we investing in the technologies, but in the particular aspect of storage that we're trying to capture, we're actually going to set a level, and we're going to make those our stochastic variables. Now, within the period, you can operate very, very differently. And so this is where we would substitute to some extent other technologies to actually make sure we get it, but we can set or have the model as a first stage decision variable, choose those levels appropriately for us, and we'll do that independently of the scenario. It's a first stage decision. Okay, I think this is without this feature in the model, our model was unable, from a planning perspective, to reproduce the features that we had saw in the simulation from Fulton. So that's critical. So that's the first stage decision. The second stage is now we're going to here, first of all, think about an expected second stage cost. That cost is going to be determined by the cost of operating. Y's are going to be my operating level, and the value of lost load is V of Q. How do we choose the value of lost load? So we have supply exceeds demand, except for we have a little bit of lost load here. That lost load is clearly going to be less than or equal to the total demand, and that then goes up into my objective function. Cool. So just it's non-smooth, but we're just using standard constraints to actually model that. Now then, in terms of the wind and the run of the river, so the water, both of this reservoir system actually has two types to it. Some of it is dominated by the fish guys, and some of it is dominated by the energy guys. So the fish guys say that the water coming in has to just run through. You can generate electricity, but it's run of river because fish dominate. The hydro guys, or the stored hydro guys, which we're going to use as our giant battery, say that we can actually control that. So for the run of river is very much like wind. So we don't really have control, it's a random event. And so we actually have to worry about here the capacity or the power constraint. So I actually have a constraint here which is a power constraint, and we deal with the stochasticity in that level by generating data, a distribution of data, which are these mu k's, which are data which is the scenarios that we're going to generate based upon that level of uncertainty. It is a power constraint, and that power constraint can deal with wind and run of river. For reservoir inflows, the stored hydro, well then we're not interested, we're worried about the chance of a dry winter, and here we're interested in an average constraint or energy constraint, and so we actually say that the total energy is less than or equal to some random distribution which encounters dry winters and all of those effects multiplied by the weather, and then we have this ability to change the storage as I've talked about before. So to some extent, to deal with the uncertainties at different levels, we have different classes of constraints, and those classes of constraints are still in a two-stage model, invest and then operate, but the richness of those different scenarios is incorporated into different types of constraints to deal with different constraints at different timescales. Okay, so that is the model that we have at this stage, and it works. Okay, so in addition to these constraints, we now add the constraint which is the environmental constraint onto this reduction, and if you think about reducing average CO2 constraints, then you can see this goes 50, this is about a quarter, this is about a tenth, and this is even smaller, and then you can drive down to zero. So if you impose the constraint that we want to reduce CO2 to zero, then without those costs that I showed you a little bit before, you can actually impose that constraint. What happens if you don't impose the constraint on CO2 emissions, but you listen to the politicians and impose a different constraint? Well, they have a whole bunch of different types of constraint which you could think about imposing. You could think about imposing a constraint, the blue constraint here, which is capacity, shut down plants. And so we'll say that the theta term here shuts down plants. What happens then? So what plants are you shutting down? I have to tell you what are non-renewables and renewables. Well, you might have an idea on that, and the government might have a different view on that, and so how you populate those sets or the data of this is subject to this. You can think about operation, so you could actually think about operation. So instead of thinking about the capacity, I have all of these non-renewable plants, I'm going to operate them. I might not operate them all of the time, and now what I would like to say is the total amount of operation is less than or equal to some fraction of the amount of operation in 2017. Or the operation gets, the YK here in the green constraint, gets converted by a factor beta K into CO2 emissions, and then you could talk about the expected value or the average value of emissions right now being less than or equal to 1 minus theta times the average amount of emissions in there. So cool, there's three different types, the blue, the green, and the orange constraint, which actually we could impose alternatively. And then you could do some other things, because we're all mathematicians and probabilists and everything. We could impose those constraints, instead of imposing those constraints on average, we could impose those constraints almost surely. So we could put a constraint which says that we're going to do it in every scenario as opposed to talking about the average. Does that make any effect? Or we could use a risk measure, or we could use chance constraints or something like that. So that's what I'd like to spend a little bit of time thinking about now. But blue, green, and orange constraints give you the following solution. Okay, so we've already seen the green solution. The green solution moved the level of CO2 reduction down to zero, and it was okay to do that. Now, what about the blue? The blue is the capacity reduction, and when you think about the capacity reduction, yes, the capacity reduction does lead to a reduction in CO2 emissions, but it's fairly modest. Instead of going from something like 1.75, whatever it is, million tons or something of CO2 emissions, instead of going down to zero, it goes down to about 1 million tons. And that's the problem, is that the definition of the data is that some of these renewable technologies are actually carbon emitting. So geothermal, for example, generates a lot of carbon emissions, and CCS, which was supposedly a renewable technology, ends up with generating carbon as well. It reduces it, does it more efficiently, but you actually get a different distribution. So the point is that if you want to go 100% renewable, make sure that you talk about the constraints as modeling what you want to do, as opposed to saying that I'm going to perform a particular action. So instead of performing the action about closing down plants, which we've seen doesn't necessarily lead to reduction of CO2, you can impose those constraints. And if you have to make trade-offs, as a government necessarily might have to, then at least be aware that those trade-offs are costing you in terms of emissions. Cool. What technology choices we do? So I'm here, this is solutions for capacity reductions. So I'm as Danny said, I'm a plumber, so I like to see results from the plumbing. And so here's a technology again. The bottom here tells you exactly as we drive towards 100% renewable. But here we're talking about capacity reduction. And the nice thing about capacity reduction is the amount of capacity that you have to invest in essentially remains fairly constant. So if you do maybe the wrong thing, which is the capacity reduction, this is hunky-dory in that it's actually cheap because the actual capacity that you have to invest in is actually relatively constant even as you drive to 100%. You see that the amounts of non-renewable within the system is driven out as we go up to 100% renewable, and that's being replaced by CCS, geothermal, wind and batteries. I should note that we spent a considerable effort in trying to model different types of batteries. So we have the notion of a slow, a medium and a fast battery. And so slow batteries actually are cheaper, and they act, as people were talking about earlier in this week, they act in shorter time frames, but those were the ones which were within our model, which were being determined to be added to our system, even in this capacity reduction scheme, to deal with what the hydro could not deal with in terms of the volatility of the wind. So to some extent we're seeing the batteries as a top-up mechanism, as a battery, because remember we have this purple or this pinky purple color, which is the hydro system, which is a whopping great big battery in New Zealand. You can think about that. So fairly constant capacity, but if you wanted to go to CO2 reduction, you actually see something different. So when you see to CO2 reduction, remember we have to get rid of the geothermal, because the geothermal is a carbon emitter. And so we end up installing a lot more, as we go to 100%, we end up installing a lot more wind. I think, and then we end up using even slow and medium-sized batteries, and also getting some solar coming in. So right at the end, between 99% and 100%, we have to knock out the CCS, because in here we're imposing the CO2 reduction. At 100%, so we have a rich portfolio, but as you see, the amount of capacity to deal with the uncertainty in this thing rises up pretty strongly. But we're mathematicians, and so this is the slide that nobody else put up. So there's a carbon price. Okay, so if I have this model here, I've imposed a constraint. I can think about taking the multiplier on that constraint, and I can tell you what that multiplier is, and that multiplier will be a carbon tax. Okay, or I could just use a Lagrangian exercise and stick it up into the objective function and parametrically change that, which is what I did here. So I changed the parameter, so that this is a carbon price going from 0 right up to 1600, and if I were able to choose those values appropriately, I could make this picture look identical to that picture. That's what we all know from our 101 optimization class. Okay, what's the bad news is that this value, or somewhere around here, is probably the palatable value for carbon tax. And in order to get anywhere near my 100%, and this is really much closer to the portfolio that we're getting at something like 90% or maybe 95%, once you get to that thing, the carbon tax is probably not politically expedient. And so we can talk about our models as being informative, and as I say, nobody else has put up these slides just because I think everybody else knows that these values are really huge in terms of carbon tax in order to affect to 100% renewable or large-scale values of renewability. I think these are important. As I say, this is dependent upon the particular data that we have, but I think it's instrumental and would carry over to lots of other things. And then you can see that, in fact, if you use even a big price of 1600 carbon tax, you still only get to a reduction in there, which is about somewhere between 95 and 99% renewable. And so that the costs associated with driving down to 100% renewable, while we can do it, and the costs don't look very big, the effects on the rest of our economy could actually be substantial. So what about, I've talked about an average constraint here. All of those constraints were average. They're expectation less than or equal to 1 minus theta times the original value. So we have expectations here. What about almost sure? So if you do almost sure, if you impose the constraint almost sure, then the blue lines don't change. The blue is a capacity reduction. That's a first stage decision. So if you change what you're doing in the second stage, it's not going to change it. So the blue line stays hunky-dorily exactly the same. Okay, but now what happens is if you impose a constraint, instead of saying it on average, the average emissions have to be going down across all of our scenarios, however we've generated that rich collection. Instead, we say that it has to be occurring in every scenario. Then what happens at low levels of reduction, you get significant changes. Because at high levels, you're already investing in renewable technology in order to get the reductions that you need. But at low levels, you actually have a bunch of scenarios here, which some of them will be very expensive in terms of carbon emissions. And so we see here, in particular, if you look at the orange bar at the business as usual, suddenly it goes down to about 125 if you impose the for all constraint, the almost surely constraint, as opposed to the constraint over here, which is a constraint which says the average amount of emissions. So I don't know. It turns out that there's a single year, 2005, which suddenly sucks up all of our benefit at the average constraint and does a huge amount of reductions and emissions in 2005, and that is okay if you do an average constraint, because in all of the rest of the years you can see that you actually reduce less. So be careful. I think the warning is that there are significant differences at low levels of CO2 reduction, and what the constraint that you impose can significantly change the solutions that you have. So what about a normal hydrology year? What is a normal hydrology year? So Andy says that he thinks that a normal hydrology year says that in 50% of the years we should have no emissions, and then the other 50% of the years everything's okay. So that's a chance constraint. So the probability that we impose the constraint is going to be less than, is going to be at least 0.5. And so you can run that model, and if you run that model and you impose that constraint, so we all know how to model chance constraints. We have to introduce integer variables, and we have a mixed integer programming problem, and then lo and behold, 2005, 2007, there's 1, 2, 3, 4, 5, 6. So I was using historical data as my scenario data here, and so in 6 of the 13 years that I used, we actually had non-zero emissions, and in the other 7, boom, we went down to 0. And this was the portfolio of technologies that we used, so mostly wind, a little bit of battery. We then looked at an increased demand. So what happens if there's an increased uptake in New Zealand of electrical vehicles? So the only difference between these pictures and these pictures is we actually have a different estimate of demand, which incorporates a behavioral assumption that changes what people, the uptake within New Zealand of electrical vehicles. So when there was more electrical vehicles, actually what was stunning to us was actually the emissions that we got were almost identical. The bad years were the same bad years, and the amounts were about the same. And the reason is that if you look at the portfolio, the distribution of the technologies that you actually use somewhat more. Instead of 1,200 capacity, you have to have nearly 1,600 capacity. And so you have a capacity which is more rich in everything. So I have another nemesis here, right? So average level of emissions go down, right? So the last thing is I'm in a session with risk-averse solutions. We modeled within this this optimization model, system optimization model, the notion of a system-wide risk measure. And as you see, both in the reduced demand or the standard demand and the increased demand here, you get very similar distributions, although the same things that I pointed out before happen. The key point, though, is that the amount of wind installed, so gray is the amount of wind installed goes down as you become more and more risk averse. And so because you replace that with CCS, then this is a less risky technology, and so the overall amount of capacity that you have to incorporate is a lot smaller. Total cost, so I've actually shown you, I haven't shown you this picture yet. The drive to going towards 100% in renewables does get expensive, particularly if you go after CO2 emissions. Okay, how do you pay for this? Okay, so if you want to pay for this, I claim that we've already been told how to pay for it this morning. We need to convert our system optimization problem into an equilibrium problem. And the difference in the equilibrium problem is now that each of the agents, if you think about the agents as being fossil, renewable, transport, or demand, correspond to agents with a different risk measure. And we talked about how you would populate that. The model that you would have then clears is an equilibrium model, as Yves was talking about, a complementarity model. The complementarity model has all of these independent agents optimizing their two-stage stochastic programming problem with pricing in each of the scenarios and pricing on that energy constraint happening. If you want more details about how we use this, I have my nemesis over here saying I have to get off the stage, and so I will tell you about that independently in another or offline. So what would I like to leave you with? 100% renewable electricity has several interpretations. Those interpretations, if you think about capacity reductions or CO2 reductions or energy reductions, lead to different solutions. The policy should choose the objective function and not the action. So that was advice that we gave to, at least to some people who were thinking about these problems. Uncertainty in the model makes a difference, and I showed some average solutions. Those were were motivated originally by some out-of-sample testing and using that to actually get error bars. So before you all ask me the question, to get those error bars, we would do an out-of-sample testing, and Andy will talk about that tomorrow. And the next stages are to go to a multi-stage and an equilibrium counterpart and give you the results on that the next time we're here. Thank you very much.
So I'm the stand-in nemesis. We have 3 minutes, right?
Yeah.
This was my strategy, my PhD exam. I talked the entire time, and there was no time for questions.
Yeah.
They still passed me, and will pass you.
Good.
Models are for insights, but also for numbers. I loved an insight, and I'm going to ask about a number. So
yes.
the insight, the idea that, carbon emitting capacity is clearly bad, so let's lower that. That could conceivably increase emissions if you lower carbon, because you have to operate it more ahead of time. I didn't quite see in the last graph whether indeed that happened or whether simply it was just turned out to be ineffective. But that possibility was a terrific insight.
Yeah, and that does happen in our model. So with those constraints, we actually, with the water levels, those water levels do actually reproduce exactly those effects in the planning model as well as the simulation
And do you
model.
actually get, when you lower carbon emitting capacity, do you actually get more total carbon emissions? Is it that perverse?
So when we
So cut
yes.
carbon emitting capacity in half and suddenly the emissions go up.
Yes.
Okay.
And that was more generic than we had believed.
Terrific insight. So numbers, so if we go cost and CO2, ignoring when the emissions take
Yep.
place, what year, ignoring the learning externalities that
Yep.
Professor Newberry talked about in the costs and so forth, your cost is going to look highly nonlinear if we look at the efficient alternatives. And what I'm curious about is, this is where the numbers come in, how inferior are your other policies, in particular the capacity constraint policy or the megawatt hours constraint policy? Are they way the heck off the frontier, so we got hugely more emissions and costs than we could conceivably get, or were they close to this cost frontier?
So the trade-off is, so there is a trade-off, and I was trying to get at that in terms of the capacity that you have to install. When you actually do capacity reductions, the overall capacity that you install, because you are talking about different things being renewable, is actually, the cost is actually lower.
The cost is lower, but the emissions
But
are
the
also
emissions,
different.
but then you have have no recourse to drive those emissions down to zero, because that's your capacity is still 100%. There is no.
So what I'll suggest, Michael, is that this distance, how far you are from the efficient frontier, is something interesting to calculate.
Right.
And if it's minuscule, then maybe it doesn't matter which policy. But if it's huge, those are terrific arguments against the inefficient policies. And I'll sit down.
Thank you.
Okay. Yeah. Maybe time for a couple of questions. Yeah, right at the back.
So I'm sorry to go back to the issue of weather and climate again on this, but you have 12 years worth of data there, and you're talking about the probability of having no CO2 emissions in 50% of those years. And I realise you mentioned at the end the idea of doing an out-of-sample testing of how robust this kind of stuff is.
Yep.
Have you any idea of how you go about getting that out-of-sample data for 2050, for 2030, 2040? I mean, this is going to rely on some sort of model projection again. So there's kind of a lot of uncertainty.
So there is uncertainty in the data. I don't know. I could. So Andy has some more detail on the operational details of how those simulations were run. They were based upon the historical data that is available. So predicting out in the future is not something we've looked at, but I think it's something worthwhile to be considering.
Maybe I can take another question and talk a bit afterwards.
Yeah.
Vitor?
So when you're defining the 50%, so when you're defining a normal hydrological year, right?
Yeah.
And you define that's going to be 50% where you are not going to have any carbon emission. What is happening with your initial state? Because depends where your reservoir starts. That can make a whole lot of difference in which would be your
Right. So we
right?
have so we model this as a circular constraint. So we actually do have and we allow the optimization to choose that initial value. Now, if with the out of sample testing, you actually know the data, which is the initial levels within that scenario, then you could fix that and then choose the values to modify it. It doesn't really make a lot of difference where you sit this, because to some extent the only thing which is important for the model is the difference in levels. And so as long as that none of those levels hit a lower or an upper bound, then we can adjust the initial level up or down at the beginning of the model and not affect it, as long as it doesn't hit one of the lower or upper bounds. So I don't think the model is sensitive to the choice of that initial value.
I think we're going to have to wrap up to go to the next speaker, so we'll take questions offline then.